The game changing, supercritical, transformational electric power pilot plant at SwRI will demonstrate the future of energy, a more efficient and cost effective method of producing power. What is supercritical carbon dioxide and what makes it a better way to power up? That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast presented by Southwest Research Institute. Hello and welcome to Technology Today. I'm Lisa Benya. Our guests today are SwRI engineers Dr. Tim Allison and Dr. Aaron McClung. They're talking about the $112 million, 10 megawatt supercritical transformational electric power pilot plant, or STEP pilot plant at SwRI. The plant will demonstrate supercritical carbon dioxide technology, which promises lower cost, lower emissions electricity. Thank you for joining us today, Tim and Aaron.
Good morning.
Thank you.
I think a key word in the name of the STEP pilot plant is transformational. So how will supercritical carbon dioxide potentially transform how we get our power? What would you say is the big picture potential of this technology?
So I'll take a first stab and then let Aaron chime in. I think fundamentally the biggest difference with supercritical CO2 power cycles is that we're replacing steam or air, which typically is used as a working fluid in power cycles, with high pressure CO2. And that's fundamentally different in the way that the machinery and the heat exchangers will be designed. And that introduces some technical challenges, but also a host of potential benefits for some of the ones you mentioned, Lisa, and it works for a lot of different applications.
Jumping in real quick, the change of working fluid allows us to tailor the cycle. So a cycle is basically what components do you put together, what temperatures and pressures do you get it to turn thermal energy or heat into working energy or mechanical energy or power. So by making the shift to carbon dioxide, it allows us to tailor the cycle, the components that we're putting together to generate power for a wide variety of applications beyond what steam and gas turbines can be used for. So it opens up a lot of new pathways to produce power at higher efficiencies, which really, you can almost substitute higher efficiency for lower emissions.
Okay, so let's continue talking about the STEP pilot plant. And the facility is on the grounds of SwRI in San Antonio. So why is the STEP pilot plant being built? When will it open?
So right now the pilot plant is on track to be operational in about early 2022. And to get there, we just finished constructing a brand new building, and that building is going to house all the infrastructure, the natural gas heaters, the cooling towers, the electric grid connections, load banks that we use to proof hardware, but also the power cycle. So the turbine, the compressor, all the piping, the control valves, the heat exchangers are put in the building. Right now, many of those components, those custom components, the first of a kind, are still in fabrication. So as they arrive, we'll be installing them into the building, piping them up, installing instrumentation, putting the control system together, and then commissioning through the rest of 2021 and into early 2022. The goal or objective for the facility and the demonstration project is demonstrating the potential of CO2 power cycles. So to date, the concept for the cycles have been around since the 1930s. Early implementation in the late 1990s and early 2000s. But these were at small scales, kilowatt scales. And the challenge is CO2, because of its properties, means turbo machinery is small, heat exchangers are small. And at small scales, all your secondary losses add up. So we're demonstrating the cycle is at 10 megawatts electric, or 10 megawatts. And that's kind of hitting the cusp of it's a commercially relevant demonstration. So the turbine's commercial size, the heat exchangers are commercial size, The compressors are commercial size using commercially relevant technology, the components, the seals, the design. So the objective for this project in the facility is put all those components together that have been developed individually. We've run compressors, we've run turbines, we've run heat exchangers, but this project puts them all together to actually produce power and demonstrate, do we match our predictions? Does everything behave the way we think it's going to behave? When you're operating commercial scale hardware, what breaks first? So now we know what needs to be addressed before you go to your first commercial product. So that's really the objective of the facility, to demonstrate the overall system, demonstrate the component technologies, and make sure we know how to operate it and what kind of performance we get out of it. So what kind of benefit can be applied long term.
So when you say you're demonstrating it, who are you demonstrating it for? Who's your ideal audience here to see how this technology works?
So the ideal audience. So at the end of let's take a step back. So this project is a collaboration. It's a collaboration between Southwest Research, Gas Technology Institute, or GTI, who's a project prime, and General Electric. We're kind of the three main project partners who are executing the project. The project is being funded by the Department of Energy. So right now for this project, the client is DOE, and DOE's interest and the various partners' interests are demonstrating the commercial potential. Because at the end of the goal, this project is for DOE, but the end results will inform GE, GTI, other commercial companies, what the potential is, what's the benefits, what do we need to do? Because at the end of the day, you have to get the commercial partners and equipment manufacturers, but also utilities and operators on board that supercritical CO2 technology can effectively and cost effectively offset steam or offset gas turbines for power production.
Are you talking about use in power plants, homes, businesses? When you say commercial, what is kind of the end? What's the vision that you have for it?
So the vision that's been progressing is utility scale. So the end application would be a provider such as CPS operating a plant using carbon dioxide technology at the utility scale to provide power to their customers. So that's one vision.
Oh.
Another application is you have a steel mill or a cement plant or an industrial process that generates a lot of heat. It also has heat as a byproduct. A new market is CO2 for waste heat recovery, where you can actually work with a industrial provider to convert some of that waste heat back to power. So that's an additional benefit, less emissions. That's an entirely new market. You can do the same thing for the pipeline industry. So right now, the big focus is on utility scale. But once you demonstrate the technology, once you kind of have initial buy-in, you also have new markets for waste heat recovery. We're also working projects unrelated to STEP, but using the same fundamental technology to apply it at the kilowatt scale. And if you can apply it at the kilowatt scale, that opens it up for cars or heavy-duty trucks or actually home applications. So the fun thing about CO2 technology is it's a very broad spectrum of where you can actually apply it.
So we could one day potentially see sCO2 power just about everywhere. That's really neat. So I think one thing we need to talk about is, what is supercritical carbon dioxide, the source of this power? What is sCO2?
Sure. I'll take a crack at that one. So I think most of us are familiar with carbon dioxide. It's actually part of the mixture that we breathe is air. And our bodies actually generate carbon dioxide as we breathe out. And then CO2 can take many forms. In the air, it's a gas. You might even also notice, like in sodas or other carbonated beverages, that's CO2 bubbles that you see in the beverage. or you can even purchase CO2 as a solid at very low temperatures. So that's dry ice that you can purchase and use. And those are different phases in which carbon dioxide exists. Supercritical carbon dioxide is just a name for CO2 that's up at high pressures, so about 73 atmospheres, and above a temperature of about 88 degrees Fahrenheit. And what's special about CO2 above those conditions is it no longer will have distinct phase changes between liquid and gas. Instead, it'll have a continuous change from a liquid to a supercritical fluid. And what a supercritical fluid is it's a fluid that behaves in many ways like a gas. So it'll fill up a volume that it's in, but it has very high densities that are close to liquids. So similar to, say, water. In using that fluid then in a power cycle gives you advantages of compactness, as well as good heat transfer and good efficiency.
So, how does supercritical carbon dioxide generate power?
So we use lots of different fluids to generate power. So I mentioned earlier, steam turbines or gas turbines use water or air as a fluid, and they all work in a similar way where you run a thermodynamic power cycle, either a Rankine or a Brayton cycle. sCO2 is used in a Brayton cycle, which is just like a gas turbine. And the way that generally kind of works is that you operate a compressor, which increases the pressure of the fluid. You add energy to the fluid in the form of heat, and that can be done from many sources, either fossil fueled combustion or renewable heating. And then you take that hot fluid and you run it through a turbine, and it expands across these turbine blades and spins the turbine, which drives a generator and creates electrical current. And then you take the fluid out of the exhaust of the turbine, you cool it down by rejecting the heat through a heat exchanger, and then you close the loop. You compress the CO2 back with the compressor, and you run the same molecules of CO2 in a closed loop that way, compressing, heating, expanding, and cooling. And through that process of adding heat and rejecting heat to that power cycle, you create a positive network which can be used to feed electricity into the grid.
Let's talk about sCO2 because it's currently being used in other ways. So, how is it currently used and how long has it been in use?
So there are a variety of ways that supercritical CO2 is currently used, even at the commercial level. So one of the more popular ones is that supercritical CO2 is a very good solvent. And so it's used in the extraction business for extracting things like essential oils. It's used for decaffeination of coffee and so on. Also, it's used in the dry cleaning business. One more that is done commercially is actually when we transport CO2 in pipelines for enhanced oil recovery or for carbon capture and sequestration from power plants. The pressures that they operate those pipelines at is typically above the critical pressure. So that's supercritical CO2 as well.
And so it's been around for a while then.
Yeah, I think in terms of as a solvent, that's been around at least for over a decade. Um, for carbon capture sequestration and enhanced oil recovery, it's been certainly a few decades. There are also other applications besides as a solvent. So you don't see this too much in North America, but in other countries, um, supercritical CO2 is used as a fluid for air conditioning. It's a fluid that has a much lower greenhouse gas potential than other refrigerants that we use in power cycles. And so you'll see essentially refrigeration systems that are charged with supercritical CO2 and run a refrigeration cycle.
Yeah. But those are typically larger commercial systems for buildings or refrigeration plants.
So, what are the benefits of supercritical carbon dioxide? You've named quite a few already, but if you can kind of just sum up what's great about this particular form of carbon dioxide.
So there are several, and I'll take a stab, and Aaron, you can chime in if I miss anything. I'll start with the one that gets the most attention, and that's that supercritical CO2 power cycles can have higher efficiencies than steam cycles when you get to really high turbine inlet temperatures. And that efficiency increase means that you can get more electric power from the same amount of fuel or same amount of heat input. And that enables that reduces the cost of electricity. And so that's really attractive to everybody, from concentrating solar power renewable applications to fossil fired applications. Um, and that's a really big carrot out there that's driving a lot of interest in developing that technology. But that's not the only benefit. So there are benefits for other applications. Aaron mentioned that there's interest in using waste heat and making electric power from that. And so one of the benefits of using supercritical CO2 there is that the machinery, the whole power conversion system is actually simpler than using other fluids like steam cycles or organic Rankine cycles. The machinery and the heat exchangers are very compact because the density of CO2 is so high. And by compact, when you have a smaller footprint, that reduces material costs. It also means that you can ramp the equipment up and down a lot faster because you have less metal to heat up or cool down. So those are some of the benefits with SCO2.
And any drawbacks to this form of power?
So I'll say the primary drop. Oh, go ahead, Aaron.
I was going to say the biggest challenge right now is it's just a young technology. It's competing with gas turbines, which have been around since the 1920s, 1930s. It's competing with steam turbines that have been around for 200 years. So the challenge is it's competing with very entrenched technologies, and it's using new configurations that the marketplace isn't necessarily familiar with. So, for example, our turbine uses dry gas seals, which really come out of oil and gas and pipeline applications. It's using coatings that are coming from aerospace. It's using manufacturing processes that are not necessarily what the conventional OEMs would see for a power turbine. And that's just the turbine. So the drawbacks are making sure that we actually understand the performance and showing the performance benefit over something like steam. Those are really the current challenges with the technology, some of the drawbacks.
So you mentioned the turbine. The highest temperature sCO2 turbine in the world was created and is housed at SwRI, and you can fit it on a desktop. So will one of you tell us about this compact machinery and how it works?
Sure. So the Sunshot turbine, this was another DOE program for Office of Renewable Energy. We demonstrated a turbine design that works at 10 megawatts at reduced power. So this is basically a 10 megawatt turbine that's about 4.5 feet long. But the actual working section, the blades that convert the thermal energy into power, it has 4 rows of blades. Each blade is about 1 inch tall, and the overall working section is about 12 to 18 inches. So it's very compact. If you look at a equivalent 10 megawatt steam turbine, it's something on the order of 20 or 30 feet long. So what's different is the fluid densities. So Tim mentioned the change in properties. So if you look at air, the densities at temperature and pressure for power generation are not all that dense. I mean, it's lighter than what you're breathing right now. But if you talk about CO2 at these temperatures and pressures, it's about half the density of water. So because it's so much denser than air, the volumetric flow is so much smaller. So you can get away with a much smaller flow path, which drives the compact machinery designs.
I know the turbine, it's, you know, it's the size of the desktop as you just described. It's small, but it really holds a lot of power. And I think one thing I read is that you could power potentially 10,000 homes with that one desktop turbine. I mean, that's a lot of potential, a lot of power in one small piece of equipment. Is anything like this existed before?
So if you're talking about power density, the amount of power it puts out compared to the physical size of the object, we're talking power densities similar to the oxygen pumps on the shuttle main engine. So it's a lot of power in a very small size. So it's, from that standpoint, the closest analogy is not a steam turbine or a gas turbine. It's actually a rocket motor. So it's a big shift in how you design some of these components from what you're used to for conventional power generation.
Yeah, I'll just throw on that the design challenge that we face with this type of technology is, yeah, it looks a little bit more like a rocket engine than it does a gas turbine or steam turbine, but the rocket engines that we have on, say, the space shuttle main engine had to last for several minutes, whereas this has to last for 30 years in a power plant. So you have this intersection of all the design challenges of different classes of machinery.
But that's one of the fun challenges of working on something like this, is because you're taking bits and pieces from a lot of different technologies and applying it. So you get to pull design concepts from aerospace, you get to pull design concepts from oil and gas, you get to pull design concepts from conventional power gen, and you have to figure out how to make it work. So these are some of the fun challenges.
Yeah, it's really cool and how it's all coming together, and there's just a lot of future potential for this technology. So, is this something you see? And I know you mentioned you want to get this into the commercial space and in use for utilities. So, potentially, could this be powering all of our homes someday? And if so, how far off is that?
It definitely could be. So it has the efficiency potential. The challenge for implementing it is commercial acceptance. So there are commercial OEMs out there that are working on waste heat recovery products, and they're working on designs and trying to get and working through first customers. So that's probably on the horizon of 3 to 5 years for lower temperature waste heat recovery applications. And as those systems operate, you gain operational experience and you gain comfort, and the operators gain comfort. So then there's a little bit more appetite for risk. So then you can, once you have confidence that the fundamentals work, then you can apply it to primary power. One of the challenges or opportunities is the shift away from coal-fired units to natural gas peakers, the integration of renewables. So there's a lot of flux in the power generation market. And CO2, in my opinion, is actually well placed because it can work with indirect cycles, it can work with CSP, it can work with thermal energy storage. So there's a lot of places that changes to the market. CO2 technology is actually well suited to be a good fit for that market niche. So that's waste heat recovery on 3 to 5 years, primary power probably 10 to 15 years, but there's a couple of applications like energy storage, which are brand new markets that could fill the gap between those 5 to 10 year points.
One of the exciting things about supercritical CO2 is that it's applicable to a lot of different energy sources. So we've talked about renewables with concentrating solar power or geothermal, using existing waste heat. Those are all zero emission type technologies. And I think sCO2 is well situated to take advantage of those. We also have probably what's a challenging and long road to transition away from fossil fuels, and sCO2 helps out there as well. So sCO2 has the improved efficiency and lower cost that we look for that leverages fossil fuels. There's even flavors of supercritical CO2 that can do zero emissions with a fossil-fired application. So it's really uniquely situated to be advantageous for carbon capture. There's just a lot of different spaces where sCO2 offers advantages.
What has been your biggest breakthrough in developing this technology?
So I'll talk a little bit about our general experience with supercritical CO2, and then Aaron can discuss some specifics to the STEP project. Over the past decade, SwRI has worked on over $120 million worth of projects on supercritical CO2 power cycles. And those have included advanced cycle development, as well as working with a lot of different components. So we've advanced heat exchangers for these applications, turbines, compressors, machinery components like rotating seals. We've developed new combustor designs or combustion technologies for supercritical CO2. And we've done that at a variety of scales, from very small systems that would do waste heat recovery on a vehicle engine at the kilowatt scale, all the way up to seals for utility scale turbines working at the hundreds of megawatts. You mentioned our work on the desktop sized turbine, and that's really been a big breakthrough for the technology and supercritical CO2 industry in general. When we validated that turbine design, we ran a full temperature and a full pressure test back in December 2018, and those were at conditions of over 1,300 degrees Fahrenheit at the turbine inlet and 250 atmospheres of pressure at the turbine inlet. So very extreme conditions. It was a pretty exciting test to run. You could see, the turbine casing is essentially glowing red at that point. And we did that with a lot of success. So we demonstrated that we could accurately, the design that we developed with GE Research was able to contain the pressure well. It was able to manage the thrust on the machine. The rotor vibrations were really low and well within acceptable limits. And we had good thermal management on the turbine to protect all of its low temperature components. So all of these really critical first of a kind design features were proven with that unit. And it was the first supercritical CO2 turbine to run with temperatures really anywhere close to that. And that's really important for the whole industry, because it showed that you could successfully translate all these on paper advantages over to a real piece of hardware. And then once you gain confidence in that, that allows us to move forward with essentially the next generation of that design for Aaron's project, which is the STEP turbine facility.
Yeah, so breakthroughs that really kind of enabled STEP were demonstrating the turbine under Sunshot, demonstrating compressor operation under EERE Apollo, some of the initial system studies that tell us how to put everything together that were performed by SwRI, GTI, and others. So those are kind of some of the supporting breakthroughs. On STEP itself, the challenge and the fun part is taking all those independent breakthroughs, the compressor operating by itself, the turbine demonstration at reduced scale, and putting it all together. Because the full-scale operating plant doesn't necessarily look like a test stand. It really is a very big test stand, but it doesn't necessarily look like what we do at reduced scale or reduced power. So I think the biggest breakthroughs to date are working through the detailed design of putting all the different components together, because they all interact. One of the challenges are the way the compressor operates determines pressure and temperature elsewhere in the system, the way the recuperators are designed, impact ramp rates and how we start up and shut down. So just working through all the details and the nuances to put a functioning system design together, I think has been the biggest breakthrough or lesson learned so far. And then we're also putting together all these first of a kind components. So the breakthrough is putting the system design. The challenge is actually implementing the system. So dealing with small design challenges on the turbine, small design challenges on the compressor, detailed design challenges with some of the recuperators. We have all these little tasks that have to be done. They have to be done kind of in lockstep to make sure that the operating system will work. So that's probably been the biggest challenge to date.
So this final question is for both of you, and I can really hear your enthusiasm about this pilot plant and about this technology. And, my question is, how does it feel to be on the inside developing this new, cleaner source of power really from the ground up? Is this rewarding work?
So go ahead, Aaron.
So yeah, it is rewarding work. It's challenging work. It's rewarding work. It's been fun to be in on the first implementation, on the first scale up, working through all these different detailed design issues or challenges, and you have to deal with them one at a time to make sure you get through them all. But the rewarding part for me is seeing it all come together, and actually, I'll give a shout out, seeing my team work through it, because it's not just Tim and I working on this project. We have about 7 people dedicated to STEP, and we're just at Southwest, and we're bringing in 7 to 8 other people for detailed skill sets. So we have a large team that's working on this project, and watching the individuals grow as they're learning the system, watching the system to come together, and then watching the technology is where I found the biggest reward for this project.
I think it's really exciting. I think we still see so many potential applications where sCO2 can develop into, and I see so much potential there, and that's pretty exciting to be involved in. We're clearly, with our efforts on STEP and other projects, SwRI is a leading center of expertise on sCO2 technologies in the world, and I'm really proud of the team for that. There's also a lot of pressure. So when we receive a big award like the STEP project, we get a lot of eyes on us to make sure that we do a good job. And I think that pressure is motivating and exciting. And the team's doing a good job with it.
Yeah, a lot of eyes on you and the STEP pilot plant and the sCO2 technology. So it is an exciting time, and there's so much to look forward to with this new pilot plant coming up at SwRI. So we say it often on this podcast that our scientists and engineers are changing the world, and you both really are proof of that with introducing this new form of power with so much potential. So thank you for joining us and telling us all about it today.
Thanks,
Thank
Lisa.
you.
And that wraps up this episode of Technology Today. Subscribe to the Technology Today podcast to hear in-depth conversations with people like Tim and Aaron, changing our world and beyond through science, engineering, research, and technology. Connect with Southwest Research Institute on Facebook, Instagram, Twitter, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SwRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.